Hi everyone, welcome to this tutorial on out-of-distribution detection. This is Sharon Lee from the University of Wisconsin-Madison. It's a great pleasure to co-organize this event together with my wonderful co-organizers. And especially I want to thank Andre for all the effort leading things here and making this happen. In this presentation, I'll walk you through some research challenges and recent progress that has been made in this exciting field over the last couple of years. Though I couldn't make it to ICCV in person due to some traveling difficulty, I promise you that the tutorial would be equally exciting. So let's get started. I would like to start the talk by showing you this video. This is a model trained on the Berkeley Deep Drive or BDD dataset, performing bounding box tracking on the road. Despite the great performance shown in this demo, the reliability of our machine learning models can often be challenged when we deploy them into the real world. And in my research, my mission is to encourage researchers and practitioners to take a cautious view at the methodologies we've developed, especially be aware of the unexpected and unknown situations that the model wasn't trained for. To give you a concrete example, we took this image from a dataset called MS-COCO, which is completely different from this BDD dataset, right, that we use to train these self-driving car model. And then we run this image through this model trained on BDD. And so concerningly, you can see that the model trained on this self-driving car dataset can produce overconfident predictions for this unknown object, which is the helicopter in the middle, to be a truck. And keep in mind that this helicopter was never exposed to the model during training time, right? So in other words, deep neural networks do not necessarily know what they don't know. This phenomenon has raised significant concerns on models' safety and reliability. As you can imagine, algorithms that just blindly classify these out-of-distribution samples into one of the irrelevant categories can be catastrophic. And ideally, we want the model to be able to flag such scenarios, say, I don't know, or abstain from making a prediction so that humans can intervene and take precautions. And this kind of example can manifest in real life, causing real consequences as well. For example, here I'm quoting this news article from last year, which reported that a Tesla vehicle using the self-driving mode crashes into a private jet. And so what's happening in this video, you can find this online, is that the white car is driving towards this blue jet, and the jet starts spinning around. Unfortunately, no one got injured in this event, but you can imagine the gravity of similar incidents, right, in real life. And so obviously this out-of-distribution detection problem has become very, very important. And this is going to be the focus of this tutorial today. So before we get started, you might be wondering, how do we define out-of-distribution data? So let me first provide a mathematical definition for it. Let's say we have our training data distribution, which in this case is a mixture of two Gaussians for simplicity. So we have class label y equals to 1 and y equals to -1. And our in distribution Pn would be defined to be the marginal of this joint distribution over this input space. So in other words, that's what the green contour is highlighting here in this figure. During test time, these orange dots could emerge, which are out of distribution from an unknown or novel class that doesn't belong to y equals to 1 or -1, and therefore should not be predicted by this model because of the class is irrelevant to what the model was trained on. So to translate this toy data into some higher dimensional data, such as natural images, you can think of CIFAR10 on the left-hand side being the in distribution and SVHN being the OOD, which have disjoint labels from the left-hand side. And so SVHN is just one of the OOD data sets that a model would encounter. And there are, of course, many other ways that the unknown would emerge on this data manifold. So as illustrated on the right side of this slide, you can imagine this to be the natural image manifold that one could possibly encounter or generate on this internet. And so this is in sharp contrast with the left-hand side, which is the task-specific data set that the model was trained on. And so out-of-distribution detection is, in fact, a non-trivial problem. And I want to use a few slides to explain to the audience what the challenges are before we dive into some of the technical solutions. So the first challenge is the lack of supervision from unknowns during training time. Typically, the model is trained only on the in-distribution data, in this case, the green and blue dots, using, say, empirical risk minimization. And you can't really anticipate where these unknowns, in this case, the orange dots, could emerge in advance, because there can be a huge space of unknowns. And what I'm showing you here is just in a 2D space, but you can imagine that things get exponentially more complicated as the dimensionality grows. And this problem is further exacerbated by these high capacity neural networks that we're working with nowadays, which can have this amazing power in terms of fitting on a given training data distribution or a task. But unfortunately, they can produce quite problematic decision boundary for the purpose of OOD detection. Or in other words, they can't reliably distinguish ID versus OOD. So to explain what I mean, let me use one of my favorite toy examples here. So as shown in this bottom figure here, let's consider a classification task with 3 class conditional Gaussians. So we have class 1, 2, 3. And it turns out you can train a very simple neural network. It doesn't even have to be complicated convolutional or transformer networks. You can just take a multi-layer perceptron and fit this task almost perfectly to achieve almost 100% classification accuracy. And so here's what the decision boundary looks like. So essentially learns this triangular shape decision boundary, right? So all the points that's on the bottom left part will be classified as class 1, and similarly for the other 2 classes. So at a glance, you would probably notice that this decision boundary is sufficient if we just care about distinguishing among these 3 classes. However, it's problematic when it comes to OOD detection. For example, if you look at all the points in those red region, which are relatively far away from our training data distribution, but nonetheless, the model is producing highly confident predictions on those points, right? All the red regions. So that's why this decision boundary is problematic for OOD detection. And so one last challenge is that real-world images are composed of numerous objects and components. And therefore, we need finer-grained understanding of OOD at the object level, not just image level. And over the years, we have seen this surge of interest in this challenging problem space. Really, it's great to see a thriving literature on OOD detection. And so in this survey, my collaborators and I try to cover and summarizes the methods that have been developed in the space. I won't be able to get to every single one of them in this talk, but I'll try to unpack some of the important methods in this tutorial. So this is the structure of today's tutorial. I have categorized into 2 parts. In the first part, I'll talk about inference time out of distribution detection, mostly provided with a pre-trained neural network. How do we design OOD scoring functions to separate ID and OOD data? And then going beyond inference time methods, I'll talk about how we can design better training time algorithm that can better regularize neural network for optimal OOD detection performance. So let's start with the first part, which is inference time OOD detection. To give you a method overview, a model is typically trained on the in-distribution data. So in this case, say Cypher10, using empirical risk minimization. And so the training objective would minimize the average loss across all the training populations. So once the model is trained, we're going to take the network as it is without modifying its parameters. And so during inference time, for any given input X, our goal is to devise a scoring function S that we can use for OOD detection. Essentially, this scoring function would allow us to partition all the points in the space into 2 parts. If it's above the threshold, we're going to consider it as ID and produce the class prediction label. And otherwise, we'll flag this to be OOD for further inspection. So in other words, we're performing a level set estimation here. And the advantage of inference time, or sometimes we call post-hoc OOD detection, is that it doesn't interfere with our original task, especially when the model is already being running in production scenario. So in this case, the model is guaranteed to have the same performance in classification while having this additional safety layer almost for free. And I also want to mention that this problem is different from anomaly detection, which is also a classic problem in machine learning that often treats all the data points as one class without necessarily differentiating the class labels. So in our case, our goals are twofold. We want to be able to train an accurate classifier and at the same time, a safeguard to defend against OOD points. So how do we define OOD scoring function? This question has really driven a very rich line of works in this field. And so today, I'm going to primarily focus on 2 types of inference time approach. One is using output-based method, and the other one is distance-based method. So let's start with output-based methods. A common output-based method or baseline is to use the softmax confidence score. And so the definition is given in this equation here, which is essentially the largest posterior probability, right, among all the prediction scores. However, if we zoom into, look at this distribution of maximum softmax probability across all the ID and OOD samples, we would notice that the maximum softmax probability is non-distinguishable, right, between these two types of data. So this plot is actually based on a real neural network trained on Cypher10 as in distribution and evaluated against SVHN as OOD. So you see here this highly overlapping area between these two types of data make it very challenging to effectively separate these two types of data. And this phenomenon is also related to the fact that neural networks can produce overconfident predictions on OOD data. And so instead of using softmax score, we brought forward this energy-based out of distribution framework, which has the core idea that really influenced many of our recent works and other researchers as well. Compared to the confidence score, we show that energy score is better suited for OOD detection. So here's the high-level view. We have this input X that's going through this neural network parameterized by theta. And then after this, we'll calculate the energy score, which I'll talk about the definition in the next few slides. And based on this energy score, we can then perform a similar thresholding-based comparison. Just want to note here in this figure here, we flip the sign of energy because energy is usually lower for ID data. So we plot in this figure the negative energy on the x-axis just to align the convention that larger score indicates more ID-ness and vice versa. Here, the threshold can be chosen based on our in-distribution data, for example, at a 95 percentile. So let me give you some further details on how we define an energy and how is that related to OOD detection. So this idea of energy-based model was first introduced to machine learning in the 80s and has been around for decades. To give you some background, an energy function would take an input, say my cat, and then a corresponding label y. And then it would produce a scalar known as energy. So this energy essentially measures the compatibility between an input, x, and this y state. And it should give a lower value if it's compatible in this case. And this function can be non-probabilistic. We can turn this into a probability distribution using the Gibbs distribution, which would produce a normalized probability for a given input to be associated with this state y or label y. And so again, this is the same Gibbs distribution that we saw in previous slide. If we look at this denominator here, which is also known as the partition function, it essentially takes the integral over all the possible y's. And by equalizing these two sides, the free energy can be expressed in terms of the negative of the log partition function here. And so this notion has been around in physics for a long, long time. So how does this notion connect to neural networks or more closely to OOD detection? So it turns out that a neural classifier can be interpreted from an energy-based perspective. So let's consider this neural network, which is producing output logit, F1, F2, and so on. And so this is pre-softmax output, right? And then we can normalize these output by the softmax function, which you have seen in this talk before. So this would produce a normalized probabilities across all the classes that sums up to 1, right? And so now if we define energy function E of x comma y to be the negative of this logit, effectively, this turns into something that we just saw earlier, right? That's the Gibbs distribution. So you see this symmetry here between the two sides. And recall this is how free energy was defined. Now, in the context of a neural network, the free energy replaces this integral with the summation across k discrete classes. And so now for every input x and a pre-trained neural network y, these free energy can be calculated very easily using the log sum exponential operation. And so with energy scores, the distribution between ID and OOD data would become much more separable, as highlighted in this slide. And I also want to kind of, put the two definitions side by side so you can see the clear mathematical difference and contrast. So the first line highlights the posterior probability, which is what softmax MSP is defined upon, right? So it's essentially the maximum among all the P of Y conditioned on X. On the other hand, energy score is defined to be the negative log of the denominator in our softmax function, right? And interestingly, if we rewrite this posterior probability to be the joint probability P of X comma Y divided by the likelihood P of X, you can see that energy function, in fact, has an inherent connection to the log likelihood. And this is fundamentally closer and more desirable for the purpose of OOD detection, right? And so, in other words, energy score is at least, one step closer compared to this, more suitable OOD detection function that we need. And we'll come back to this notion in the second part of this talk as well to discuss this aspect further. Cool. So now we can look at and evaluate these two approaches. Here we train a network on Cypher-10 and evaluate it against SVHN. And so the performance is reported in terms of FPR. So in this case, the FPR measures the fraction of OOD data that's misclassified as ID when the threshold is chosen so that 95% of ID data is above the threshold, right? So lower FPR is better. And so with softmax score, we see that the detector is making a very high error, around 50%. So it's not making a very effective differentiation here. And in contrast, using energy score can reduce the FPR more effectively down to 35%. And so the distribution become more separable. And here are the evaluation results on a kind of more diverse range of OOD datasets considered. And the blue bars indicates using softmax score, and the green bars indicates using the energy score. So across the board, we observe a consistent improvement using energy score. And I also want to mention that the score is hyperparameter free, which is easy to use in practice as well. So that's for output-based methods. And next, I want to switch gear a little bit and talk about this distance-based approach as well. So the idea of distance-based methods is often operating in this feature space, right? Recall the output-based methods kind of relies on this very end of the neural network, right? The F layer. And for distance-based method, we're going to shift our attention to this feature representation space. for example, highlighted in this image here. And one of the representative or early distance-based method is called Mahalanobis distance, which essentially models the feature space, say from the penultimate layer of the neural network as a mixture of class conditional multivariate Gaussian distribution. So one for each class, right? As highlighted in this figure here. And then during test time, this method uses the distance to the closest centroid as a proxy for OOD measure. So the definition of the score is given at the bottom of the slide here. Intuitively, an OOD sample should be relatively far away from all of these class embeddings, and ID data will be at least close to one of those class centroids. So that's the idea of Mahalanobis distance. And this approach is considered as parametric. And so it actually suffers from some major limitations. The first one being the strong distributional assumption that's being imposed here. And in practice, the feature that's obtained by a neural network may not always correspond to a Gaussian distributed. For example, here, what I'm showing here is the actual embedding based on a T-SNE visualization that is extracted from a model trained on Cypher 10. And then the gray is the OOD data distribution. And so you see that for some classes, the embeddings are actually now Gaussian distributed, which is suboptimal. So to mitigate these limitations, recent distance-based approach has shifted towards this non-parametric view. And a popularized method is based on this idea of k-nearest neighbors, where a sample is considered as OOD if it has a large KNN distance with respect to the training data, and vice versa. And so this approach does not make any distributional assumptions about the underlying embedding space, and therefore it provides stronger generality and flexibility. Moreover, this paper also showed that the KNN approach can in fact benefit from a compact and well-learned embedding space. And so to learn such optimal representations for OOD detection, especially for distance-based OOD detection, this paper introduced CIDR, which is a novel representation learning framework that exploits this notion of hyperspherical embeddings for OOD detection. And so by hyperspherical embeddings, it means all the features live on this sphere as shown in the slide here, and all the embeddings have uninorm, right? Equal distance away from the origin. And so in particular, CIDR jointly optimizes two losses to promote ID-OOD separability. I won't go into the details here, but at a high level, there's one loss term called dispersion loss, which intuitively would promote a large angular distance among different class prototypes or class centers. And then in addition, there is a loss called compactness loss that would encourage each sample to be closely aligned with the corresponding class prototype, right, based on the ground truth label. And so compared to directly using off-the-shelf contrastive laws such as SubCon, it turns out that using CIDR in conjunction with KNN distance shows much more competitive performance as illustrated in this table here. In this slide, you can also see that the embedding learned by CIDR, which is on the right-hand side, enjoys much better compactness compared to the embeddings learned by cross-entropy loss on the left-hand side. And moreover, the classes are distributed more uniformly in this space, highlighting this efficacy of dispersion loss. So if you're interested, I would recommend checking out the papers for more details. So far, I have, talk about, quite a bit about the inference time OOD scoring functions. In particular, we've covered both output-based methods and some representative distance-based methods. But these scoring functions is only part of the solution. And in my view, mitigating OOD risk really requires us to rethink the learning algorithm design from a training time perspective. And so now let's move on to the second part of this tutorial, which will focus on this training time perspective for OOD detection. And in particular, I'll first talk about this high-level learning objective design, and then move on to some other aspects related to this. To really kind of explain the necessity or the importance of learning algorithm design, let's revisit this example here. Here, the model is trained using ERM, or empirical risk minimization, on the in-distribution data only, right? And recall that the decision boundary is sufficient for distinguishing or classifying the classes, but they're insufficient for OOD detection purposes. And the reason is because existing learning algorithms are primarily driven by optimizing the accuracy only on the training data, but they don't account for the uncertainty that could arise from outside data. And so going beyond these, standard cross-entropy loss, what we really need is this training time regularization that can explicitly account for uncertainty from outside the ID data. And so that the decision boundary, the ideal one, should look like the right-hand side, right? Which is much more aligned with our underlying data density, right? That's compactly surrounding these in-distribution classes. So the question is, how do we go from left to the right-hand side without actually, having to perform density estimation, which is often very, very intractable. And to do so, one promising idea is to adopt the safety-aware learning objective, right? Which is a combination of the standard cross-entropy loss that minimizes the risk on our ID data. And then additionally, we have this regularization term that tries to separate ID versus OOD. And so now let's zoom into this regularization term here. So for now, let's assume we have access to some auxiliary outlier training data. And later on, I'll try to relax this assumption. So our idea here is to explicitly push the energy score to be apart between the ID versus OOD data, thresholded at 0, right? So it's basically as highlighted here, for all the in-distribution data, we want to push the energy score to be as below 0 as possible. And so that means the negative, if you flip the sign, that means the score should be above 0 to be on the right-hand side. And this objective has some nice mathematical interpretation too. Recall that energy has this inherent connection to this negative log of this softmax, negative log of this likelihood, right? And so essentially we're performing a level set estimation based on this measurement related to energy score. And that allows us to shape this entire space into two halves. It's in fact a simpler objective to optimize than having to estimate every single point, the P of X for every single point in the space. So in other words, it's a lot more tractable than performing density estimation. So the result of the training is more separable distributions measured by energy score on the right-hand side. You can see that the FPR can be further reduced quite substantially once you have this training time regularization. And the left two figures are based on the model trained with cross entropy loss that doesn't have such explicit regularization in place. And so this looks all promising, but it does have, one caveat. Because works like outlier exposure requires us to, have this auxiliary outlier data for training. But the question really is, how do we obtain, where do we even get those data from? In practice, collecting a large outlier data can be arguably very expensive. And you can imagine this requires some manual data collection and cleaning, because you have to make sure that, the ID data doesn't really overlap with this auxiliary OOD data. And this process needs to be repeated every time you switch ID data to be something else, right? So it's not a really flexible method. And so you can ask this question of, how do we obtain these auxiliary OOD training data automatically for free? And so that's why I also want to introduce this line of approach on virtual outlier synthesis, which is really kind of designed to address these limitations in the original outlier exposure work. So the key idea of virtual outlier synthesis is to sample low likelihood data points in the feature space for model regularization. And this is important because synthesis in this high-dimensional original pixel space can often be intractable. And in contrast, adopting this feature-spaced view can lower this dimensionality much more effectively and making things more tractable. And this suits our purpose because we care more about regularizing the model's decision boundary. So to explain how the approach works, we can first model this feature representation space, in this case, the penultimate layer in this neural network, as a class conditional multivariate distribution. And so here, basically, we can empirically estimate the mean and covariance matrix, mu and sigma, based on our training samples observed. And then once these mean and covariance matrix are estimated, we can sample a lot of those, right, automatically from such parametric distribution. And then we would filter out those points with low likelihood. We would consider those to be our desired virtual outliers, right? Because they would lie kind of outside this, this ID region. And we can do this for every class in our ID data. For example, these 3 clusters corresponds to 3 distinct classes in this embedding space. And the dark points indicate the generated virtual outliers, which we call V. And so once these points are synthesized, now we can take these synthesized virtual outliers and pass them through this fully connected layer and obtain this output, FV. So essentially FV is just basically a linear transformation between the synthesized virtual outlier with this linear weight. And with this output, we can calculate the energy score, right? Energy is defined as follows, which depends on this log of summation of exponential of these logit output. So now putting everything together, we can now train this model by using the ID data together with the virtual outliers. And essentially the objective would try to push the energy score of virtual outliers to be above 0. And on the other hand, to reduce the energy score for the ID data to be below 0. And this is nice because we're not utilizing any auxiliary or external outlier data set, and everything is just operating on this original training data set and distribution itself. And I also want to mention that VOS is a general learning framework, which is suitable for both object detection and image classification. In case of object detection, this overall learning objective would have 3 terms. So in addition to classification and this uncertainty regularization, we also have this localization to try to localize where the boxes are. So now coming back to this example I posed earlier in this talk, where this helicopter is misclassified as truck with high confidence. And if we, train our neural network with this explicit uncertainty awareness, it turns out that we have a much better chance of detecting those successfully as unknowns or as OOD. And going one step further, I also want to mention that, admittedly, one of the limitations in VOS is the strong distributional assumption that's being made in the feature embedding space. And so we mitigated this in a follow-up work at ICCV 2023 called non-parametric outlier synthesis. So the key idea really is to change how the virtual outliers are sampled without making any distributional assumptions about this embedding space. And so you can work with, embeddings of any arbitrary geometry and offering strong generality and flexibility. And beyond synthesized outliers, you might also be wondering, is there any way what if we want natural outlier training data for free? Is it possible to do so? So the answer is yes. One of the promising, I would say, direction paradigm is to leverage this wild unlabeled data, which I'll explain next. So what do I mean by wild data? Let's say you have trained a model using, based on self-driving car task, right? To detect cars, truck, pedestrian, bicycle, and so on. And then you're going to roll out this model into the real world. And then the car is going to start receive all kinds of, frames as it drives on the road. And among these frames, there would be data points that are either belonging to categories that the model has been trained on, but also, right, some of the novel classes would emerge. And so it's really kind of a heterogeneous distribution that contains both known and unknown. So the advantage of this, leveraging wild data is that it's very cheap to collect these points. Basically, you just let your model run in its operating environment, right? Then you gather all these data points basically for free as they comes in. And every single point is unlabeled. You don't have to, annotate any one of those. And importantly, these, wild data often has a much better match to this true test time distribution than using, data collected offline, which, may or may not generalize to this actual test time OOD distribution. But the challenge is also quite notable. As I mentioned, wild data is heterogeneous. And so mathematically, it's a mixture of distribution of both in and out, right? So you can express this marginal distribution of P wild using this equation as follows. And so an interesting research question really is, provided with, a clean labeled in distribution along with a large quantity of this, wild, but nonetheless impure or heterogeneous wild samples, how do we effectively learn this OOD decision boundary? Because we know part of this wild data actually contain our true OOD test time distribution. So I won't go into the details here, but I do want to point out some useful references or recent works that attempted to formulate this problem more in a more mathematical way and put forward, solutions, initial solutions for this setting. So definitely check them out if you are interested in learning more about the existing solutions for this more realistic setting. Cool, so that's all I have prepared for this tutorial. Just to recap, in this tutorial, I have walked you through some interesting research challenges for OOD detection. And on the methodology side, there are two broad categories of methods we've talked about. One is focusing on the inference time provided with a given pre-trained neural network. If we can't make any changes to this training process, how do we devise an effective scoring function that can separate ID versus OOD data? And two representative lines of work considered output-based methods and distance-based methods. And then going beyond, I think it's very important to keep in mind that training time regularization is needed in order to mitigate this problem more fundamentally. So I have introduced this safety-aware learning objective that brings in this uncertainty awareness during the training time that can more effectively regularize the model's decision boundary between ID and OOD. And so within this kind of paradigm, one notable challenge is where do we collect this OOD training data? And so there are two promising approaches, one that is based on synthesizing virtual outliers, and the other one is to leverage these wild unlabeled data for model regularization. So hopefully you have found this tutorial to be informative and useful. If you have any further questions, please feel free to send me an email or follow up with me. So here's my email address. And thank you for watching, and I hope you enjoy the rest of ICCV.